So what have we seen up till now? We have an estimate for the error between the exact solution of the boundary value problem and the approximate solution we get by the finite element method. We measure the deviation in the 1 norm, in the H1 norm. And the error estimate says the following. We can estimate this error under several assumptions, namely, what are the assumptions? First of all, we only look at spatial dimensions up to 3. And furthermore, we assume that our exact solution, where is it? It's not, is in hk plus 1. K a natural number, so at least the solution that is the minimal regularity requirement which we have, the solution is at least in H2. H2 means, under these assumptions on the dimension, that we have continuous functions. That is what we use, at least in our technique, by means of the interpolation operator. So this is what we need. And this K appears at another place, namely here. We require, this reflects the local amount of degrees of freedom, the local accuracy of the consistency error, if you want, the local accuracy of the method. We require that the full space of polynomials of degree up to k is contained in the ansatz space on the element. We have, on all the elements, we have the same ansatz space in the sense that we assume a family of triangulations, and on this family of triangulations we always have affine equivalent elements. We discussed that we can extend this to a finite amount of different families if they match together. For example, matching, say, biquadratic approaches at the triangles with at a transformed rectangle with the quadratic approach at the triangle. Okay, so this determines the k, and this k is reflected then, okay, here on the right-hand side, the semi-norm k plus 1, the highest order derivatives of the solutions appear. This makes sense. This is by assumption a finite number. And the assertion is there's a constant c, which may be computed in some cases. In general, it's a generic constant, but independent of u and independent of h in particular, depending on everything else which determines the problem, the domain, the coefficients, whatsoever, such that we have an estimate saying we can estimate the error by this constant times h to the k times the seminorm of k plus 1 seminorm of the solution. So we have a k, to say it short, we have a statement that there is an order of convergence of order k. K coming here from the polynomial ansatz space under the assumption that the solution is smooth enough. So, and that is important to keep this in mind. At least that is what this theory says. Maybe what could do better, of course, but this theory says if we want to take an advantage of higher order methods, if we are not satisfied in taking linear ansatz on the triangles, we take quadratic ansatz, with the consequences of, first of all, basically a doubling of the degrees of freedom, and on the other hand also of a more dense population of the matrix, which enhances the amount of work we have to do for solving the emerging set of equations. Then we have to make sure, according to this theory, that this makes sense, that we can really benefit from this higher order, and that would mean here that the solution has to be in H3, not only in H2. And this, of course, opens up a lot of questions. If one thinks, for example, at a simple thing like an elliptic problem at a rectangle or a cube, something which is convex but has edges, then the regularity theory for elliptic problems says there is H2 regularity if the other things are well behaved, if you only look at the influence of the domain now. So there's a question mark according to this theory. We can of course think that this theory can be improved, and there may be only if the regularity of a solution goes down only locally. This is what we expect on such a domain with edges. We would expect that in the edges or close to the edges, irregularity goes down. That is what we checked already at an example. But we would expect maybe that away we would have still a smooth solution, and then it may well be that this is also reflected in the actual behavior of the method. So one really has to think about which type of order of convergence one is using. But this line of thoughts maybe also says maybe it makes sense to not only to have h as a variable in the method. That is the way we look at finite element methods. There's also a notion saying we are looking at h refinements. But you can also look at p refinements. You could say, okay, I keep my mesh as it is, but locally I increase my degrees of freedom if I think that locally this makes sense according to this discussion we have. Of course, in our setting, this must be done in a conformal way. I cannot just refine on one element in the sense of increasing the degrees of freedom and let the others as they are. So there are some problems involved here, which is not the case with more modern Galerkin methods, but that would also be a possibility. Okay, but this is only an outlook, and now we want to discuss what we have here. I have not mentioned one of the very important assumptions which we had to make, namely the shape regularity of this family of triangulations. What was this? It was a requirement that there is a constant, here denoted by sigma, a positive constant, independent of the h, so valid for the full sequence, for the full family of triangulations, such that we can estimate the rho k, that was the supremum of the diameters of all inscribed balls, by a sigma times hk, which was the diameter of the element. So it's not possible that that the elements get flatter and flatter, meaning that the rho k goes to 0, but they keep the same size, meaning that the hk stays constant, more or less. So this prevents us from using types of elements which would make sense in using in discretized very thin layers, which might come up looking at sort of laminated materials with thin layers in between. So what we are going to do now is we would like to discuss this requirement of shape regularity, see that in a two-dimensional case, for triangles and the linear ansatz, so that's quite restricted, we can do better in the sense that we can formulate an alternative condition on the shapes of the triangles, which is not so restrictive. That is one part what we want to do, and finally we will ask the question, okay, this is now all in H1. If we now are a little bit more moderate and say we want only to have an estimate in L2, so only for the deviation of the function values, not for the derivatives, can we do better? Do we get a higher order estimate? And directly we cannot get this, because the Sayers lemma only connects the finite element error with the approximation error of the space in the H1 norm. We already know, if we go back and now not look at the consequence for the finite element method, but for our intermediate result, which was concerned with the interpolation error as an estimate for the approximation error for the underlying finite dimensional space, we can see we can do this in all kinds of norms up to the order k plus 1. And we see what we expect if we go down in this m, we go up in the order. In particular, if we go to m equals to 0, then we would get the full order k plus 1. That means for the linear ansatz in the on triangles, we see from here immediately in the L2 norm the approximation error of the interpolant is h square. But this does not help us immediately, because we have no connection in the L2 norm between the approximation error and the finite element error. Okay, a further remark for further considerations is Where is it? If we look again at this estimate, which was the basis for deriving this estimate for the interpolation error, and which was the basis for the requirement of shape regularity, where we got this quotient in and we said, okay, this quotient has to be bounded such that we get no deterioration of the order of convergence which we would like to see. You see, this is true for the case m bigger or equals to 1. In the case m to 1, if you only look at the interpolation error in the L2 norm, this shape question does not appear. So this is just here 1, this term here. So keep in mind that only for looking at the interpolation error in the L2 norm, we don't need any shape requirement. So if you that means if we go to look for alternative requirements, substituting the shape regularity, we only have to look at the H1 semi-norm. The L2 norm is okay in any case. So let's first discuss, before we do that, let's first discuss what the requirements of the shape regularity is. At the first glance, it's a little bit disappointing. For example, if we look at the case of the affinely transformed unit cubes, let's look at the situation in 2 and in 3 dimension, and we only do not look at parallelograms, but at rectangles with side lengths h1, h2, h3, which without loss of generality are supposed to be ordered like that. Then, of course, the h3 basically, so what is then the diameter is just the Euclidean length of the vector of the h's, because that is the connecting vector between the 0 node and the most far away positioned node h1, h2, h3. That is one thing. And the other thing, what is the diameter, the maximal diameter of an inscribed ball? This is determined by the smallest of these values. So if we look at the quotient, we get this type of expression, either in 2D or in 3D. And that would mean to bound this requirement, we would have to have something which we will later on call quasi-uniformity. We would have to require that again, then we have something like the maximal, in this case, the maximal of the side length of the length has to be can be estimated by a factor times the minimal length. Such that we can vary the size of the elements, but they all stay in a fixed. The relations all stay in a fixed range. Fixed always means for all h, for h going to 0, of course, not for a fixed triangulation. For a fixed triangulation with a finite amount of elements and nodes and anything, we can fulfill every requirement. So this looks quite restrictive. The good thing is that actually, so we would require something like this here. We would have to have an alpha such that also the largest one can be estimated by alpha times the smallest one. The good thing is that this is not necessary, that in this case we can derive these approximation error estimates directly without doing the transformation, and therefore we avoid this question of shape irregularity. The shape regularity comes in from our approach: first go to the reference element, do the things there, and then go back. And if we can avoid this, if we can work directly on the element, then we have the chance to come up with another condition or to avoid this condition totally. And here in this case we can avoid it totally, so actually it turns out we can allow for any rectangles. That is one remark. This is good because it would prevent us from doing some such anisotropic refinements that would prevent us from refining in one direction and keeping the other directions as they are, which might be reasonable for such thin layers as I indicated. So, for example, in this case, what we would like to do is, we discussed this thing, I think, already. So what we expect here is that the variation in the solution and also in the gradients, the fluxes, are much larger in this direction where the material changes rapidly. Let's say the K2 is much, much larger or much, much bigger than the K1. Compared to this direction here. So this means what we would like to do is we would refine in this direction, but not so much refine in this direction. So we would like to do very thin rectangles for an appropriate triangulation. And what I said is, in the end, this is allowed. The problem comes if we say, okay, we would not like to work with rectangles, we would like to work with triangles. Then we have to take this very thin rectangle and make two triangles out of that. So to speak, we have to do a Friedrichs-Keller triangulation. But this is at the moment not allowed, and this we will see in a second. For seeing this, we now have to discuss what it really means, what this shape regularity really means in 2 dimensions for triangles. So let's do this. Okay, so we look at this generic geometric situation. We have here HK is the longest edge of the triangle and is also the diameter of the element. Then we have here the minimum angle of the triangle. We denote the corresponding node by A1 and the others by A2 and A3, and by H2 the height situated here at HK. So this is the geometric setting. Maybe I can freeze it that we can see it for further reference. Okay, so if we go back to the estimates, to the terms which come in from this back and forth transformation, we get in powers of A norm of B, of the matrix of the transformation, and corresponding, and powers, other powers of the norm of B to the -1. And what we did up till now, we handled them in the spectral norm and the norm induced by the Euclidean norm by means of these 2 estimates, and that means we would get in basically products of this type, which has to be handled in some case, and these products were then, as by these estimates, HK over rho k, and that was the place where we came in with the shape regularity. So now we try to be a little bit more precise and look directly at this product without doing this estimate here immediately. So, and we are free to choose the norm. The change of the norm in this 2 or 3 or a d-dimensional space just changes, brings in a constant, depending on d, of course, but depending on nothing else in this estimate. And now it turns out to choose the Frobenius norm. You remember what the Frobenius norm is? No? The Frobenius norm, so we have on the tuples we have the Euclidean norm, and the induced norm is the spectral norm. A norm which is related to the Euclidean norm on the matrix would be just do the same thing. That is, take all the squares, or the squares of the module, sum up and take the square root over all elements of the matrix. That is the Frobenius norm. And that is a norm which is compatible with the Euclidean norm. So it has the submultiplicativity property. So norm of A times x can be estimated of norm of A times norm of x, but it's not the induced norm. It's bigger than the induced norm. It cannot be the induced norm because an induced norm always has the property that for the identity operator, that is for the unit matrix, it has to be 1. But what is the Frobenius norm for the identity matrix? Take all entries, in our case, square root of t, square root of the dimension. Yeah, and this is not 1, up to the one-dimensional situation. So it's something different, but we are free to choose that. Why do we do that? Because in the Frobenius norm, we have a close relation between the norm of this 2 by 2 matrix and of its inverse. These are the two matrices we have to deal with. Why is this? What happens if we do the inverse in 2 dimensions? Okay, first we have to divide by the determinant of B. That is what we do here too. And what do we do here in the matrix? You remember how the inverse of a 2 by 2 matrix is computed? What do you do with the matrix apart of dividing by a determinant of the matrix? You should know that by heart. Okay, what does one do? One exchanges the positions on the diagonal. Okay, doesn't care in which sequence we compute the squares. And one puts a minus to the off-diagonal elements. Also, we don't care about that. So we have this relation here between the norms, and we take advantage of. Okay, then we have this relation. The determinant of B, we discussed this already. This is the the volume, the surface of the corresponding parallelogram. So half of it is just the volume of the triangle. And the volume of the triangle is, as we remember from school, length of one of the sides times length of the height divided by 2. So this is what's written here. Okay, now let's compute the Frobenius norm. The Frobenius norm in general can also be phrased in saying, okay, I have the columns of my matrix, and I take, looking at the Frobenius norm squared, I take the columns of the matrix, take the Euclidean norm of the columns, and add them up. Of course, I could also do the same thing with the rows. But here the columns are more convenient because the columns of the matrix B are just the connecting vectors between the nodes. So we have this relation, and this, of course, can be trivially estimated from below by hk squared. This is just this quantity here. So if we now take all this information we have up to here and look at this product, so what do we get? So we get 1 over determinant, we get this square here, so we get an h square here, in estimating from below, and we get this here for the estimate of the one in the estimate of the 1 over determinant, and so in the end we get this lower bound here, hk over the corresponding height h2. Now, how is this? If we look, unfortunately I cannot point to the left screen. It only works on this screen here. This is too magic, this presenter. So, but you see this picture, and you see also the corresponding triangle with a right angle, and on the left-hand side. And how is this? There is, what we see here is, what is then here? We have H2 to be the opposite leg, die Gegenkathete, and we have the Ankathete, the adjacent leg, which is a part of HK. And what is the relation between these two and the angle? what do we have to do? For example, if we look at the cotangent of the angle, this is then the cosine over the sine, and this is then the now the adjacent leg over the opposite leg, and the length of the adjacent leg can be estimated by hk, so we have this estimate here. So using this estimate, we get a lower bound for the quantity which we are concerned with, namely the cotangent of the minimal angle. With similar estimates, we can also get an upper bound of this product by 4 times the cotangent of the minimal angle. That is, this critical product, which we have to handle, and which we up till now handled by this, by saying an upper bound is bounded by this shape regularity requirement, behaves exactly as the cotangent of the minimal angle. So if we want to have this quantity bounded, that is a necessary requirement. This comes from this condition. Up till now, we only dealt with sufficient requirements, but now from here we see it's a necessary requirement in this restricted two-dimensional situation with a triangle that we have the cotangent of the angle bounded, bounded from above. What does that mean? Or now, if we now go to the first of all, what does that mean? When is the cotangent bounded from above? First of all, the angle, the minimal angle, it just means that we have to stay away from 0 with the angle, because the cotangent has its asymptote, its singularity at 0. So that's a requirement on the smallness of the smallest angle. You have to have a uniform lower bound for the smallest angle. And as we can also now, because we have here, for this term, we have the upper bound with this quotient of hk by rho k, we see if we have shape regularity, then the cotangent bound is a consequence, but the more precise requirement is here the cotangent bound, and we cannot get rid of that. If we want to bound this product, we have to bound the cotangent. That it means we have to have a uniform lower bound for the minimal angle. And therefore, this requirement in this situation is also called the minimal angle condition. Yeah, this is not so good, because this says what we really want to do in this thin layer, taking these thin rectangles and subdivide them again, that's not allowed. Because the smallest angle, if we refine in the y direction, the smallest angle gets smaller and smaller by this. Okay. So, summarizing it, we see for triangles, the shape regularity just means the minimal angle condition. It's both, it's on the one hand side, it's a consequence of the minimal angle condition. On the other side, if we really go along this line we went up till now with having with the transformation as we did it till now, this necessarily brings in the norm of the b in the norm of the b minus 1, and then we stuck with this term. So we have to do it somewhat different. We have to omit to some extent the transformation to the reference element. And doing so, we can come up with an alternative condition which is not so prohibitive in many situations. That is then the so-called maximal angle condition. What this means, we will see. So, okay, maybe I tell you immediately what it means. In the maximal angle condition, it says what is not allowed is that the maximal angle approaches pi. So if we stay away with the maximal angle from pi, everything is uniformly, everything is okay. And that means for this example we have in mind with this very thin triangles, but which have a right angle, and the right angle is the maximal one, everything is okay according to this condition. But to prove this condition, we have to apply a little bit more detailed work. Okay, so the idea is now to prove we are in 2D, we look at triangles, and in the end we will assume that the largest angle is bounded away uniformly from pi, and then we still can show the corresponding error estimates for the interpolation error, and then by Thea's lemma we are done. And I said already, if we now look again at the interpolation error, it's not necessary to look at the L2 norm. The L2 norm is okay, nothing appears there by the transformation. We only look at the H1 semi-norm. So we do that. So we have three things to do. We have to look again at the estimate for the transformation. Be more precise there in the estimate, not directly with a norm of B. And for the back transformation, and then in the middle, we have to be more precise with the estimate for the interpolation error at the reference element. So only looking at the semi-norm means we only have to look at the derivatives. Okay, here we have now 2 being in R2, and the L2 norm of the deviation of the derivative. And what we had up till now, we were able to say, okay, there is a constant such that we can estimate this term, these two terms, by a constant times the H2 semi-norm of the corresponding function. So what kinds of derivatives are involved in the H2 semi-norm? So all derivatives of second order. So this is 1, 1, 2, 2, 1, 2. And what is now better with this estimate? Here we say we can do a similar thing, but here we only have, and this upper bound, which I just mentioned, that applied both for the first derivative and the second derivative in the L2 norm. Now we can separate the situation. So the idea is now to separate the directions as strongly as this is possible. Also, a triangle is something which does not really separate the directions. That is the problem we have to deal with. So what can we do better here? We are dealing, say, with the first derivative, and here only the H1 semi-norm of the first derivative appears. So here we have only 1, 1 and 1, 2, but no 2, 2, and correspondingly the other way around. That seems to be a very small difference, but that is one of the building stones then for this proof. Okay, let's do the proof for that. And to simplify a little bit the notation, I now neglect all these heads here indicating the reference element. And the idea is, again, to use Bramble-Hilbert in a convenient way. So what is now the situation? We have this triangle with these 3 special edges here, with 3 special vertices, 0, 0, 1, 0, 0, 1. And we look at 2 linear continuous operators. The first one is defined by integrating along the lower bound, the lower edge of the reference triangle. So what comes out is here a number, and this number is interpreted as a constant function. And by this, it's an element of L2 of k. So it's linear, I think this is clear, and it's continuous. Why it's continuous? We have here a part of the trace. So this is a continuous step to L2 at this boundary. And what we do here is we compute an integral. So we have to go from L2 to L1, but this is also a continuous embedding. Okay. So this operator and the corresponding, and what is F2? F2 is the same thing, but here we integrate about this piece of the boundary A1, A3, so in the y direction. Here's the x direction, and here we go in the y direction. Okay, Bramble-Hilbert now tells us this norm here not only can be estimated by C times the full H1 norm, that would be just be the continuity statement, the boundedness statement, but we can be sufficient here with a H1 semi-norm, because on P0, here we get a 0. It's clear that we get a 0 if we are in the constants. If we integrate a constant, then we get this constant, and then, of course, if we subtract this constant, we have 0. Of course, we have here now the same problem as we had before. The Bramble-Hilbert lemma is only formulated for functionals, and we want to apply it for operators. So maybe it's now was not so very. Maybe this is a little bit. This was written up historically by Professor Angermann and me a long time ago. So maybe it would be more convenient to formulate the Bramble-Hilbert lemma for operators. But now you see two different proofs to extend it to operators. So what we do here, we set up a corresponding functional by taking this part and multiplying it with FIV minus V for a fixed element V from the H1 of K. Then this kernel property is, of course, maintained. So for this functional, we can apply the Bramble-Hilbert lemma, saying we can estimate the modulus of GW by by the corresponding let's go directly here by the corresponding norms. So the norm here would be the L2 norm of this. The norm of this function would be the L2 norm of this part. And now not times the H1 norm of this part, but not the H1 norm of W, but constant. So this is what we have here. And now Bramble-Hilbert tells us we can, instead of that, we can have constant times the H1 norm. So this is what Bramble-Hilbert gives us. We can go from this part to this part. But now look here. If we now in particular choose here in this estimate G equals V, then we get here the deviation, the L2 norm squared. We get one L2 norm here, so we cancel one of these L2 norms and we get the estimate we would like to see here. That's a variation of this a little bit more simple way in this special situation to go from the functional formulation of the Bramble-Hilbert lemma to the application to operators. So in any case, we have this estimate here. And now we just have to plug in what that means. If we now plug in here the derivatives, so we take as W, we take the first derivative, say. What does that mean? What is F1? F1 means integrating along the edge, the x edge of the reference triangle, and that means this is just the value of V at the upper node, 1, 0 minus V0. This is again the interpolation of the underlying, these are also the values of the interpolation operator, and this difference is also exact as, is the exact derivative of the image of the interpolation operator, because on this edge we get in particular linear function. The length of the edge is 1, so the derivative is value at one side minus value at the other divided by 1. So we have this exact equality here. So what we see here is this identity here. Okay, what does that mean? if we now go back in this estimate, here we have the derivative. This we have to plugged in, and this we had computed. What was it? That was the derivative of the interpolation operator. So that's exactly what we want to estimate, and we can estimate by a constant times the one semi-norm of the, say, first derivative. So that means it's exactly what we have stated here. And for the other direction, we do it with the F2. So we now have improved this estimate a little bit. And now we look at the corresponding questions for the transformations. So maybe it's good to have now this triangle in view. Warum geht das jetzt nicht weiter? Es ist schön. Ach so. Okay, I made a mistake. Okay, this is this one, and let's have this in view. Okay, so this is now the generic picture we want to look at the triangle. So now we are concerned with the largest angle. So we have here somewhere our largest angle, alpha max. We denote the vertex by A1, A2, A3. Here we have H1, H2 for these two adjacent sides here. That is the notation we are going to use for a general triangle. And now we want to study more precisely the consequence of the transformation. And this is what we claim that we get out. So the first step is, of course, this is now the way, okay, we start with this one, doesn't matter, because this is the way back. We are in the reference element, and we want to estimate the H1 norm on the general element. And the statement is, what do we get here? We can estimate here by 1 over square root of b. This is a term, maybe we'd first compare with what we had seen already, that we can see what are the differences now. Where is it? It's here. So we are looking at this lower estimate here. So instead of square root of determinant of b, we get now determinant of b. I always forget about mentioning this modulus here because we always use an ordering of the notes that the determinant is positive. So this term does not look so good. We have instead a 1 over determinant of b. And here we would have a norm of b to the minus 1. A norm to b to the minus 1 would bring us a 1 over rho. So this is a critical term. So this term we avoid. And what do we get instead? Looks a little bit strange. Okay, what do we get? We get here the corresponding L2 norms of the first derivative and the second. And we get exactly the opposite lengths here. Forget about the opposite. We get here only the H2 square in front of that, and here we get the H1 square in front of that. So, okay, maybe it's not so clear at the moment that this will be of big help, but nevertheless one can try to prove it. Okay, let's try to prove it. So what do? Again, we write down the matrix composed of these two connection vectors. So that means in our notation, the Euclidean length of the one column is the H1, and of the other column is the H2. That was the way the notation H1 and H2 was determined. And now again, we discussed this already, how the inverse looks like, and now we're not interested in the inverse, but the inverse transpose. Okay, then again, we switch here those elements which have got the minus sign. They are switched again. And that means if we now do the transformation without estimating, what do we get? We get the 1 over determinant in. And here we get in the first vector. What we get in is this matrix, b to the minus t, multiplying with a gradient vector in x hat. So we have to multiply the first column with the first derivative. This is this, and the second column with the second derivative. This is this and this. So this factor we get out of the Euclidean norm squared here. So how is this? Again, we get here of this factor out from here. We get this factor out from here. I'm a little bit wondering why there is no... What is wrong here? Is here something wrong? I'm a little bit confused at the moment that there's no square here. Let's look again at the transformation formula. Maybe then we see it better. Where do we have it? For example, here. Okay, of course. So this is the formula we are applying. Okay, and here we have seen this is the one factor we get by the transformation of the integration element. Here in the b to the minus d, we have seen that we have a 1 over determinant of b, and then these three parts go together with 1 over determinant of b. 1 over determinant of b. Minus 2 plus 1. So it's okay. I've forgotten one factor. Okay, so we are at this level. So and now, okay, the statement is, and this implies the assertion. Is this clear? So what do we want to have? This is now just simple estimates which we still have. First of all, we take a square root. This gives us 1 over the square root of this guy. And then here we have to apply a Euclidean norm. So what we can do here, we could do the triangle inequality. So we get the length, Euclidean length of this guy. But this is, as we have seen, this is only a change in position and in sign. That the length of this vector is still h2. And the length of this vector is still h1. So we get those factors. We get the corresponding Euclidean norms. And then still we have to estimate the mixed term, which we get out by taking the square, but the mixed term can again be estimated by the corresponding sum of the norms, because 2 times a times b can be estimated by a square plus b square by the theorem of Giacomo-Binomi. And this gives us then the square root of 2, which is of course of no importance, and this gives us these terms here. So these are just Euclidean norms squared, if you see here. This is really then immediate from this term here. So and now the other direction. Now we have to go back. So we have to go back again. So we have to estimate the appearing derivatives on the reference element by the derivatives on the general element. And this is the corresponding statement we are going to use here, which tells us, okay, what we get in here is hi. The I is related to this I here. Hi times hk. over the determinant squared, square root of the determinant. Again, let us compare to what is the general estimate. This is this here. Okay, this term we see here, but this is now, so here we would have now, here we would expect something like norm to be squared, so this would be an hk square, and this is now a little bit refined, this statement, as you've seen. It's also, of course, a squared, it's length times length. This is, we cannot avoid the dimensionality, or we cannot change the dimensionality of the whole thing, but the lengths are a little bit more refined. It's now hi times hk. Not hk times hk. This is a refinement here. Okay. Why is this the case? Again, we look at the transformation formula. Maybe we do it now shortly. What we have to do is we look at the transformation formula. We plug this. We plug here the derivative in, so we get this thing, and then this is just. I want if I should then now do it on the blackboard. I think you can do it on your own. You just look at this term. You try to estimate this term, and we use all the things which we have developed already. So now we have to plug the things together. And so these are the three estimates we now want to use. We first go, let's remember them again. We first go, we start here in the one norm on the general element, go to the, so this is what we apply now to the deviation between V minus interpolant of V. We end up here on the reference element, here with V hat minus interpolant of V hat. Here we now apply, where is it? This estimate. So we are here now with the corresponding derivatives of V hat on the reference element, and then here we apply the last one. This one here, giving us this term. And now we have to see how these different determinant terms, hi terms, hk terms come together. To see how they come together, one probably has to write it down. But what comes out is this relation. So what we of course further have to use is this relation here. So we have the determinant, so we have the double volume of the triangle. So what is the determinant? So that is, I think, what you also remember, the sign theorem. Stoff der Klasse 10. Weiß ich ganz genau, weil meine Tochter das gerade macht. Okay, what does the sign theorem tells us? The surface is the sine of the angle times the length of the attached sides. So this is how we relate the determinant which comes up to the h1 and the h2. And okay, I can only tell it now to you, and I don't want to spend the time now in writing it up. You really have to put these three estimates into each other, and then you see which terms cancel, and then you see the h1, h2 terms and the determinant terms come together like this, and we get the corresponding hk term, which you would like to see, and the further requirement is that this sign term comes up here. In a sense that, what do we have? Let's see. In the end, it will turn out that it's prevented that, so we're talking about the maximal angle of the triangle. The maximal angle is always bigger than pi over 3. So we have no problems that the sine becomes small if the angle becomes small. It can only become pi over 3 in the smallest way, the smallest possibility. But of course it can approach pi, and approaching pi would mean the sign goes to 0. And this term appears as 1 over sine, so we have to prevent this. And this then in the end means we have a maximal angle condition. So if we require a maximal angle condition in this sense, so we say that a family of triangulation fulfills a maximal angle condition if there's a constant alpha bar less than pi, that for all triangles and all triangulations, the maximal angle is less or equal this alpha bar. So we stay away from pi. Then we have a lower bound for the sine, and in this we have an upper bound for the 1 over sine, which appears in the overall estimate. And by this, we have saved then the interpolant estimate. By the interpolant estimate, we have saved the error estimate for the finite element error. So the new theorem is, if we have in 2D, if we have a family of triangulations made out of triangles, fulfilling the maximal angle condition, we use the linear ansatz. Of course, we have heavily used that the functions are linear. What about quadratic ansatz? We have no idea. Then we can estimate the interpolation error in the one norm by c times h times the 2 semi-norm. So that is what we would like to see. And because of this, we have the corresponding error estimate for the finite element error. Okay. Yeah. Okay, one remark is, of course, we are always here giving away information if we all in the end. So everything what we are doing is locally. This is on one element hk, and of course there and one element tk, or how do we call it? K we call the element. On one element capital K. So always hk appears for these local estimates. But then we put these local estimates together, we sum up these squares of the semi-norms, and then, of course, to get a uniform global estimate, we have to estimate the hk trivially by its maximum h. But of course, by this, we lose this local information. We could also keep this local information in all our statements. It only gets a little bit more complicated in writing. I think we did this here in conjunction with a discussion of the shape regularity. Of course, we could keep the estimate like this and saying, okay, maybe we have different sizes here, then these different sizes appear, and here the corresponding local semi-norms. Of course, now we can view differently on this estimate. You can say, yeah, okay, we now do this estimate. We estimate the hk by h because it's the worst case which determines the behavior. But of course, there's also this factor here coming in, and this factor can, so to speak, heal a little bit the situation. So this factor indicates that maybe where it is large, we need a particular small h, and where it is small, we can rely on a larger h. That's what I already mentioned, which then goes in the direction of a posteriori error estimates and of adaptive grid refinement. And the same situation as we have here is now, of course, also with the maximal angle condition. So we write the estimates in this more uniform way only for saving a little bit of notation. Okay. Okay, so L2 estimates. I mentioned already the problem. If we only look at L2 estimates, then we would expect we get more. We can get more. We compare a little bit, of course, with what we have for the finite difference method. And for the finite difference method, for methods which sort of are comparable, if we think of the Friedrich-Skeller triangulation and linear triangles, for the finite difference method under totally irrealistic regularity assumptions, we have seen order of convergence 2 in the discrete maximum norm. Now the discrete maximum norm is again something different, like a full maximum norm, because we don't have directly an approximating function in the finite difference setting, but of course we could think of something like the linear interpolant or the bilinear interpolant. And it's also not so clear how it relates to the L2 norm, but okay, for the L2 norm we would expect something similar. So we would expect for the L2 norm the h squared to see, not the h we have seen for the h1 norm. How can we do this? We cannot directly rely on the corresponding approximation error estimate. So what we do here, which is quite nice, is a so-called duality argument going back to Urbain and Nietzsche. And it brings the so-called adjoint boundary value problem into play, die adjungierte Randwertaufgabe. So what is this? So in our variational setting, a boundary value problem is given by a bilinear form and a linear form and corresponding space. That's it. Everything is encoded in these three quantities we have seen. And now, for the adjoint boundary condition, we just do the following. We now do not take our bilinear form, but we switch the positions here in the bilinear form. And by this, we define a new bilinear form. So UV, for this new bilinear form, let's call it A star or so, is not A UV, but A VU. So this means if the A is symmetric, of course, we do not change anything. In the other case, we have changed the bilinear form, but we haven't changed the properties. Of course, this is still bilinear. It is still continuous. And it's still coercive. It's still V-elliptic. For V-elliptic, this doesn't play any role. In this case, we only look at the quadratic functional then. We set u equals to v, and also for the boundedness in the continuity statement, I think it's clear that's exactly the same statement. So, as far as the general existence theorem, Lax-Milgram, is concerned, there's no difference looking at the adjoint problem or the original problem. And now we have a requirement for the adjoint problem. That is what we need here. We need a certain regularity for the adjoint problem, and we call this adjoint problem regular if the solution exists uniquely. Okay, this we have in any case if we have the corresponding assumptions which I mentioned for the original bilinear form. But in addition, we would like to have, and this is the regularity part, we would like to have that if the f is an L2 function, the f need not to be an L2 function. What we need to have on the right-hand side is a linear bounded functional on V to have a unique solution of the boundary value problem. We have seen that means, at least in 2 dimensions, we could allow for point functional, so for the infamous delta function. Not so directly in higher dimensions, because then the delta function, the point functional, is not a continuous anymore, but we can allow for more than L2 functions. And we did this already because in dealing with inhomogeneous Neumann and mixed boundary conditions, we have seen that corresponding terms come in here which are given by boundary integrals. So they are not given by an L2 function in terms of a volume integral. So this is a special case, and what is required here, that the naive feeling which we have for PDEs is really correct. What is the naive feeling? What is solving a PDE? We want to invert differentiation. And how much? 2 times. So if we start from L2, we would like to go 2 levels up. That means to H2. And that is the statement here. We require that if f is in L2, so to speak, Sobolev level 0, we solve the equation, then we get a solution not only in H1, but in H2. And we have stability, we have continuous dependence in the sense that we can also estimate the L2 seminorm. The derivatives up to 1 we can estimate in any case, as we know. We can estimate the L2 seminorm by a constant times the L2 norm of f. That is regularity. So now we can ask, okay, is there any difference in requiring this property? And we have discussed a little bit regularity of elliptic boundary value problems. We have seen that the regularity or the missing of regularity can rely on several sources. One could be that we have very rough coefficients in the problem. One could be that the right-hand side is very rough. And one could be the domain. In particular, we discussed these re-entrant corners, which in any case decrease the regularity of the solution. So if we now look at the question, what changes from going from the original problem to the adjoint problem, of course the domain does not change. So we have re-entrant corners, we have no chance to have a regular problem here. But we can allow, for example, for a convex polygonally bounded domain, there the corresponding regularity says that this statement is true. If the coefficients are correspondingly well behaved, that means they should be bounded and should fulfill the corresponding V-ellipticity requirements and so on. Basically the requirements we have posed. Another possibility is, of course, if the f is not in L2, if the f is something weaker, as discussed, then we cannot expect a solution in H2. So it may well be that in our original problem we have a right-hand side which is not in L2, and therefore correspondingly the solution of our original problem is not in H2, but the adjoint problem has this property, because the question is only the question, if the right-hand side is in L2, how does then the solution of the adjoint problem behave? Okay, so now let's get a feeling for the adjoint problem. What does change? What is changed if we look at the adjoint problem? Okay, in the symmetric case, nothing changes. If you only have diffusive forces, the adjoint problem is exactly the same problem as we had before. If we have non-symmetric parts in our bilinear form coming from convective forces, of course, things change. The term, we have a non-symmetric part, which originally was c times gradient of u times v, and now we interchange the roles, because that is the non-symmetric part is now integral of c times gradient of v times u. But look at this term here. Here we can do again what we did several times here already. We can do partial integration. So we bring the gradient as divergence over to c times u. This changes the sign, and this brings in this boundary term. What does that mean? Now we are, so to speak, back in our original formulation for the non-symmetric parts. Some solution parts where the derivative sits on times the test function, and correspondingly boundary terms. So what has changed now? Okay, the convective part has changed from here to here. So the first thing is the sign has changed. The flow direction has changed. We are now looking exactly in the opposite direction of the flow in the adjoint problem, if there is a flow. And the other thing is, we now look at this not on the formulation c times gradient of u, but on this formulation where the convective part is included in the divergence part. It's this more natural formulation which we have discussed. And furthermore, this term appears. And this term appears means that we change the boundary condition, because we have seen such a term reflects a mixed boundary condition. So which was a Neumann boundary condition before becomes a mixed boundary condition. On if there's a mixed boundary condition, it may also change because of this. That is the variation from going from the original boundary value problem to the adjoint boundary value problem. If we have Dirichlet condition, nothing changes, then and the part of the boundary where we have Dirichlet condition, this integral part vanishes and there's no change in the boundary condition. So, as I said, we expect basically the same regularity behavior for the adjoint problem as for the original problem. And, okay, this gives us the chance, in some sense, to allow for rough right-hand sides, or inhomogeneous mix or Dirichlet boundary conditions which prevent us from having an H2 solution in the original problem, but still we have this regularity assumption for the adjoint problem. So, and this is now what the lemma of, or the theorem of Aubin and Nietzsche, or the duality theorem tells us. So we consider the situations in which we have assured that there is an order of convergence estimate in the way we have seen. So for the H1 norm of the type C times H to the K plus 1 times the semi-norm under these assumptions which we had, meaning corresponding K plus 1 regularity, the pk has to be fully included in the ansatz space P. And then, what is the difference between these two? This one is the original one, requiring the shape regularity, and this one is the special one for 2D triangle linear ansatz requiring the maximal angle condition. So we are in a situation where we have these orders of convergence estimates. Then we require that the solution of the adjoint problem is regular in the way we have discussed this. And the statement is, then there is a constant that we can estimate the error in the L2 norm by C times H times the error in the 1 norm. And here we can conclude now several things. The first thing, and then maybe I have to modify a little bit what I said, maybe because this is not so well formulated. Maybe you can go back a second. Yeah, okay. I have to modify a little bit what I said. It's not so well done here. This requirement here concerning these orders of convergence theorem, this only is required for the third step. For the first step, this is not required. For the first step, we only need to have the regularity of the adjoint problem and just unique existence of solutions. So then we get this estimate 1 here. If we assume that we have this estimate 1, what does this mean? From this estimate 1, we get immediately the estimate 2. Why? Remember the very first estimate which we had. Of course, the deviation here can be trivially estimated by the norm of 1, the 1 norm of u, plus the 1 norm of UH. But the 1 norm of UH can again be estimated by a constant by the 1 norm of u. This is the very first stability estimate for the finite element method, the inherent stability of the finite element method. So what does this tell us? This tells us that also without these further regularity assumptions with which we have to go in to get any order of convergence in the 1 norm, we still get a first order convergence in the L2 norm. This is the first statement. And the second statement is, if we now have our further regularity assumptions here, and if we have the order of convergence estimates here, then of course we can apply it to this part. And in this situation which we have here, we would have got this an order h to the k times the k plus 1 semi-norm for this part. So linear for k equals to 1 quadratic for k equals to 2, and so on. And now we get a further power of k. We get a k plus 1 here. So in particular, we get h squared for linear ansatz on triangles. We get h to the 3 for quadratic ansatz on the triangles, and so on. So if we have this first result, the other twos are immediate. The question is how to show now this first result. And this is a very elegant proof done basically in parallel in the late 60s, I think, by Aubin and in France and Nietzsche in Freiburg. And the argument is the following. Okay, we look at this deviation u minus uv. This is in u minus uh. So exact solution minus finite element solution. This is in V, and in particular in L2. So we can use this as a right-hand side for a problem of the adjoint problem. And we have this is our requirement, that there's regularity, there's an existence, unique existence and regularity for the adjoint problem. So for this particular right-hand side, the adjoint problem has a solution UF. So what does that mean? It's not written down here, it's already one further step. So that would mean for any test function from V, we would have, let's call it W for a moment, we would have AWUF, this is this reverse direction in the bilinear form, equals U minus UH W. Okay? Maybe I write it down. Jetzt haben wir nicht immer ordentliche Kreide hier. Okay, what is the situation for the adjoint problem? UF solves, what is it? On the right-hand side, FV, and here, AVUF. For all the others. So now we said F is U minus UH. So we have AVUF equals U minus UHV. And now, as in every variational formulation, we are free to exploit this variational formulation by selecting appropriate test functions. And this we do if we look in particular to the test function V equals U minus UF, minus UH. This is an element here in this space. We're talking about conformal methods. So, this is written down here. So, what do we get? So we have here the F, we have here the test function, we have here the solution, we have here the test function. This gives this middle part. So what is this here? This is nothing but the Euclidean norms, the L2 norm squared here. That is the term we want to estimate. Therefore, that's the reason why we did this. But here now we can take advantage of this error equation, of this error orthogonality, saying that under the bilinear form A, U minus UH with any element VH gives a 0. So we add here a general element minus VH from the finite dimensional ansatz space and do not change anything in this term. And of course, we can in particular choose our interpolant of the exact solution. So now we go further with this term. Continuity tells us we can estimate this term by constant times the H1 norm of the first component times the H1 norm of the second component. Okay, here at this level now we apply the order of convergence estimate which we have. for the first time. So maybe I have to correct myself a little bit. I said we can do it without any assumptions. Here we have to do it. I forgot about that. So, okay, sorry, I have to correct myself. Here, but now, okay, it's okay. But this is not now not the original solution we are talking about. That is now the solution of the adjoint problem, where we have the regularity of the adjoint problem. In particular, we have H2 of the adjoint problem, and then we can here apply our corresponding estimate, giving us one order of H for the interpolation operator. This brings in the H here. Here we have used the H2 property of the solution for any L2 function f for the adjoint problem. Okay, now we have to get rid of this term, and this is now the stability of the solution of the adjoint problems, telling us we can estimate here the semi-norm by a constant, all these constants go together, times the L2 norm of the right-hand side f. But the right-hand side f is u minus UH. And so we end up with this estimate. And now you see one of these L2 norms cancelled here. And we have exactly the assertion, the L2 norm of the finite element error can be estimated by a constant times H times the L2 norm of the finite element error in the one norm. And up to this level, we haven't used any information about what the L2 norm of the finite element error is. And now going back, maybe to see it again, now we are at this level, and now we can say, okay, if we do not know anything about the L2 norm of the finite element error, of the H1 norm of the finite element error, because we don't have enough regularity, for example, if we don't have enough regularity for the solution, in any case, we have the stability. So we can have this estimate in any case. And this tells us also without further regularity, also for an H1 solution, we still have a first order of convergence. And then if we have enough regularity to get the H1 convergence, then we get one order of convergence on top in the L2 norm. Of course, overall, we need the requirements concerning the triangulations. So we have to have either the shape regularity or the maximal angle condition, because this we use already here. We have to be able to estimate the interpolation error in one way or the other, giving this result here. So it does not allow us, so this result does not tell us anything about triangulations which are out of the framework which we have discussed till now, but it gives us a further result if the solution is not smooth enough here. Okay. Good. Okay, so next step is to look again at a little bit on the implementation of the finite element error, and to bring theory and implementation practice a little bit more together. And okay, we have some gap, and this gap, what is the gap up till now? The gap is up till now we are thinking of exactly evaluating the bilinear form and the linear form. This is the basis. So we think of an exact computation of the stiffness matrix and the load vector, which of course in general we cannot do, in particular if we have varying coefficients. So this is something which we have to bring in. And there's another point. We had stated a certain procedure for how to bring in Dirichlet boundary conditions in the finite element method, and hopefully you have implemented this meanwhile. But what this procedure has to do with the theory we have, the theory said, okay, we need a function w which has this inhomogeneous boundary condition, then we subtract it, then we get a new problem, and for this we do all the theory and this corresponding part of the bilinear form appears in the right-hand side. How these things come together, this we have not yet checked. So this is something which we have to do now. So let me remind again what the situation was up till now in the theory. In the theory, we said if we have an inhomogeneous Dirichlet boundary condition on some part gamma 3, what we need is a function w from H1, any function. So this is highly non-unique, this selection, fulfilling this boundary condition in the sense of trace. And then we write the solution consisting of two parts, of a part u, now with homogeneous boundary condition there, and the part w. And we plug this in here. And this term we can also equivalently write as AUV equals BV minus AWV. So we change the right-hand side, we change the functional by this AWV term. That is what the theory says. And then, then we are in this general framework of a function space, which we use both as ansatz space, namely here the corresponding H1 functions which are 0 at this part of the boundary, as ansatz space and as test space. Otherwise, we would have here a deviation. We would have here homogeneous boundary conditions in the test space, and here we would have the inhomogeneous boundary condition. We would have not a linear space, but an affine space for the solution space. And to avoid this, we have done this transformation. But what does that mean if we now, so to speak, follow this pure theory and do the approximation? That is now the formulation where we do the finite element solution. So this is what we would compute if we would follow this directly. This is what we would compute. And our approximate solution would now be UH plus W. So, okay, the first thing is where to get this W from. Then the next thing is how to compute these parts here. And then finally, it's a little bit strange that now our approximate solution is not really in a finite dimensional space. It's an element of a finite dimensional space shifted by some function. So it depends very much on the choice of this W. We can think a little bit what we could do with this W, and maybe look only at one dimension first. So, if we look at one dimension, situation is simple. In one dimension, let's say we would have, say, here 0 Dirichlet condition and here whatsoever. It's very simple to find an appropriate function which fulfills this boundary condition, for example, this one. Now all the problems are gone, because this specific function is in each of our approximation space. If we now start in doing our triangulation, and let's say think of piecewise linears or piecewise polynomials, this function belongs to it. So actually we do not leave our space VH, or we forget about the boundary conditions in the definition of VH for a moment. But in general, we will not be able to select such a simple function. Now, if we, for example, say, we would not do that, we select this one. Then, of course, we would have this problem. What would our solution be like? Our solution would consist of a part which is here called UH, which has these boundary conditions. And then on top this one. So this would be UH, this would be W, and our UH tilde would then be, I cannot draw it, would be whatever. And now we get here a kink, whatever. Doesn't seem very practical. So what is the point? The point is we want to fulfill the boundary condition, and we don't want to disturb too much, so to speak, on the rest of the domain. So what would be the optimal situation? The optimal situation would be, of course, a function like this here and 0 everywhere else, but this not really looks like an H1 function. Okay, what could we do? We could do something like this here. As W. This looks good for this triangulation, but now if we refine, we get into problems. So this is something which we have to resolve to bring together a theory and what we do practically. In the end, it will turn out what we do is justified. It does not disturb the order of convergence. It's not exactly what the theory says, but it's something which has the same order of convergence. Okay, but this is then what we will work out next time.